Hello, everyone. Today, we're embarking on an incredible journey through our solar system, our home in space. This is a unique, dynamic, and awe-inspiring system that formed billions of years ago and continues to hold countless mysteries. We'll discover how the solar system is structured, where it's located in the universe, and why its study is so important. Prepare for a captivating dive into science and history. Let's begin. The solar system is a grand gravitational mechanism centered around our star, the Sun. It consists of 8 planets orbiting our star, along with over 200 known moons, countless asteroids, comets, and interplanetary dust. All these objects are bound by gravity, forming a complex and harmonious structure. The sheer scale of the solar system is hard to comprehend. If we consider the Oort cloud, its diameter can reach about 2 light-years, roughly 19 trillion kilometers. Imagine, if the Sun were the size of a soccer ball, Earth would be 30 meters away and would be about the size of a pinhead, while that distance would stretch for about 4.5 million kilometers. Around 4.5 billion years ago, a vast cloud of gas and dust began to collapse under gravity. A dense core formed at the center, the precursor to the Sun, which soon began to shine thanks to thermonuclear reactions. The remaining matter formed a rotating disk, from which planets, moons, and other bodies gradually emerged. This process is key to understanding how stellar systems form throughout the galaxy. Our solar system is a unique laboratory for studying the processes occurring in other star systems. Our solar system is located in the Milky Way galaxy, which contains an estimated 100 to 400 billion stars. We reside in the Orion Arm, approximately 27,000 light-years from the galactic center. This is a relatively quiet region, which has likely played a crucial role in creating conditions suitable for the emergence of life. Let's explore what spiral arms are. These are the prominent structures in spiral galaxies, appearing as bright, winding regions containing star clusters, gas, and dust. Our solar system is situated between the Perseus arm and the Centaurus arm. This position offers us relative safety, as we are distant from the galactic core, where activity is significantly higher. The solar system orbits the galactic center at a speed of about 828,000 kilometers per hour. However, a full orbit takes 225 to 250 million years. This is known as a galactic year. The last time we were in this part of the galaxy was when dinosaurs roamed the Earth. Incredibly, if you could view the Milky Way from afar, our solar system would appear as a barely discernible speck among billions of stars. Yet, it is on this tiny speck that life arose, a phenomenon we have yet to detect anywhere else in the universe. Let's look at how our understanding of our place in the cosmos has evolved. In ancient times, people believed Earth was the center of the universe. This was based on the geocentric model proposed by Ptolemy, which remained dominant in astronomy for about 15 centuries. According to this model, all celestial bodies, including the Sun, Moon, and stars, revolved around the Earth. But a pivotal turn occurred in the history of astronomy. Nicolaus Copernicus, a Polish astronomer, proposed the hypothesis that Earth is not the center of the universe at all, but simply one of the planets orbiting the Sun. This discovery laid the foundation for a new heliocentric model. Naturally, this idea faced resistance, as it challenged age-old conceptions of humanity's place in the cosmos. Copernicus thus set the stage for a revolution in astronomy. The next key phase came with Galileo Galilei in the early 17th century. Using an improved telescope, Galileo was the first to observe the Moon, revealing its craters and mountains, which contradicted the idea of its perfect spherical nature. He also observed the phases of Venus, which provided strong evidence for the heliocentric model. These discoveries validated Copernicus's hypothesis and compelled a re-evaluation of astronomical fundamentals. Isaac Newton, in the late 17th century, completed this process. Through his laws of gravity, he explained why planets move in orbits around the Sun. Newton demonstrated that gravity is the force that keeps all celestial bodies, from the Moon to the farthest planets, in their orbits. His work formed the basis of classical mechanics and enabled more precise predictions of planetary motion. From the late 19th century onwards, and especially in the 20th century, the era of practical space exploration began. In 1969, the Apollo program successfully landed humans on the Moon. With the advancement of spacecraft and telescopes, humans began to actively explore not only the nearby planets, but also the far reaches of the universe. The Hubble Space Telescope, launched in 1990, opened new horizons, providing astronomers with incredibly precise data on stars, galaxies, and other cosmic objects. Thus, the journey from the geocentric model to modern scientific understanding of the cosmos has been marked by crucial discoveries and revolutionary ideas. After getting acquainted with the main stages of astronomical development and our understanding of the cosmos, let's turn our attention to the planets closest to the Sun, known as the inner planets. These are Mercury, Venus, Earth, and Mars. They form a unique group of bodies with rocky surfaces, distinctly different from the giants of the outer solar system. Let's start with the small but fascinating planet, Mercury. Mercury is the closest planet to the Sun, and everything that happens on it is directly linked to its proximity to our star. It orbits at an average distance of about 0.39 astronomical units, which is just under half the distance from Earth to the Sun. If 1 AU is approximately 150 million kilometers, then Mercury is located at an average distance of only 58 million kilometers from the Sun. This makes it the first in line of the planets in our solar system. Mercury is a dwarf among planets, with a diameter of about 4,800 kilometers, which is roughly 2.5 times smaller than Earth's diameter. Despite its tiny size, it is denser than many other planets, owing to its large iron core. Mercury completes a full orbit around the Sun in 88 Earth days. This is its year, the shortest of all the planets. However, its day, or one rotation on its axis, lasts 59 Earth days. But due to a complex interaction between its rotation and orbit, a solar day on Mercury lasts 176 Earth days. This unusual phenomenon is due to its orbital rotational resonance. For every 3 orbits it completes around the Sun, Mercury rotates twice on its axis. This resonance is caused by tidal slowing. Mercury lacks an atmosphere, which leads to extreme temperature swings between its day and night sides. The day side heats up to 430 degrees Celsius, making it hot enough to melt lead, while the night side, receiving no solar heat, cools down to minus 180 degrees Celsius. Such a temperature contrast is one of the most extreme in the solar system. Mercury is almost entirely metallic. Its core occupies 75% of the planet's diameter, making it disproportionately large. This core is primarily composed of iron and is likely partially liquid. It is responsible for generating a weak magnetic field, about 100 times weaker than Earth's. Nevertheless, even this feeble magnetic field creates a magnetosphere that interacts with the solar wind. The outer shell, or crust, of the planet is very thin, about 20 kilometers. Mercury's surface is covered in craters formed by intense bombardment from asteroids and meteorites in the early years of the solar system. One of the most impressive craters is Calorus, with a diameter of over 1,500 kilometers. It is so vast that the impact that created it caused chaotic terrain changes on the opposite side of the planet. Mercury's exploration began with the Mariner 10 mission in the 1970s. This spacecraft transmitted the first detailed images of its surface and revealed the existence of a magnetic field. But the true revolution in understanding Mercury came with the Messenger mission, which entered orbit around the planet in the 2000s. It collected data on surface composition, measured the magnetic field, and uncovered numerous geological features. Mercury is a window into the past of the solar system. Its surface has remained virtually unchanged over billions of years, preserving traces of early planetary formation processes. Its unusual structure and dynamics offer scientists clues to understanding gravitational interactions, the influence of stars on nearby planets, and the cooling processes of planetary cores. Next, we await the next enigmatic planet, Venus, where conditions are so harsh that it is rightfully called an infernal planet. Venus is the second planet from the Sun and Earth's closest neighbor, surprisingly similar to our planet in size and mass. It is often called Earth's sister, but the similarity ends with the numbers. Venus is a true cosmic hell, dominated by unbearable heat, acidic clouds, and atmospheric pressure capable of crushing any earthly probe in minutes. But behind all these extreme conditions lies a story that could tell us how Earth's fate might have unfolded if our planet's balance were disrupted. Venus has a diameter of about 12,000 kilometers, just 5% less than Earth's diameter. The planet's mass is approximately 82% of our planet's mass, and its density and gravity are also close. If you were to stand on its surface, you would weigh almost as much as you do on Earth. Venus is located at about 0.72 AU from the Sun, equivalent to 108 million kilometers. This is closer than Earth, but not enough to explain its incredibly high temperatures. The cause of Venus's catastrophic conditions is its unique atmosphere. Venus's atmosphere is one of the most extreme in the solar system. It is 96% carbon dioxide, with a small amount of nitrogen and traces of sulfur compounds. The upper layers of the atmosphere are covered by thick clouds of sulfuric acid, which block sunlight. Because of this, Venus appears so bright and shiny in the night sky. Its clouds reflect up to 70% of solar radiation. On the planet's surface, beneath these clouds, a true hell reigns. The atmospheric pressure on Venus is 92 times higher than on Earth. This is equivalent to the pressure you would experience if you were submerged 1 kilometer underwater. If we tried to build a base there, it would be crushed instantly. Venus's surface is the hottest among all planets in the solar system, with temperatures reaching 470 degrees Celsius. This is hotter than on Mercury, even though Venus is farther from the Sun. The main reason for these temperatures is the runaway greenhouse effect, which has completely altered the planet's atmosphere and climate. At some point in the past, Venus likely had conditions closer to Earth's. Perhaps it even had liquid water on its surface. However, its proximity to the Sun led to the evaporation of water. Water vapor, as a powerful greenhouse gas, amplified the heat-trapping effect. Simultaneously, carbon dioxide released from active volcanic activity accumulated in the atmosphere, increasing its density and exacerbating the greenhouse effect. The characteristics of Venus's atmosphere dictate its dynamics. Almost 100% of the thermal energy reaching the planet is reflected. About 70% of sunlight is reflected by clouds, but the 30% that penetrates downward is absorbed by the surface and can no longer escape into space due to the dense carbon dioxide layer. This process turns Venus into a true heat trap. Temperatures on Venus are remarkably stable across nearly its entire surface, with minimal fluctuations between day and night sides or equator and poles. This is due to the high density of the atmosphere, which evenly distributes heat across the planet. Even at night, when the sun does not illuminate the surface, the temperature remains roughly the same as during the day. Beneath Venus's clouds lies an astonishing world. The planet's surface has been studied using radar, as conventional optical methods reveal nothing due to the clouds. Venus is a planet of volcanoes. Its surface is almost entirely covered by lava plains formed by past eruptions. One of the planet's highest points is the Maxwell Montes Mountains, rising to an altitude of about 11 kilometers. This is higher than Mount Everest on Earth. But most of Venus's surface is flat and dotted with strange geological formations like corona, enormous circular structures formed by magmatic activity. These corona are remnants of powerful tectonic processes that occurred billions of years ago. Despite the presence of volcanoes and lava, Venus lacks clear signs of plate tectonics like Earth. Instead, its crust tends to bend and break under magma pressure, creating unique landforms. At an altitude of about 60 kilometers above the planet's surface, incredibly strong winds blow at speeds up to 360 kilometers per hour. This phenomenon is called superrotation. The planet rotates much slower than its atmosphere. Venus itself completes one rotation on its axis in 243 Earth days. This is the slowest day among all planets. But a year on Venus lasts only 225 days. Thus, a day on Venus is longer than its year. Venus is one of the first planets to be studied by spacecraft. Soviet Venera missions were the first to send probes to its surface. Probes like Venera 7 transmitted data from the surface but lasted no more than 30 minutes due to the extreme heat and pressure. Later, the European Space Agency's Venus Express mission studied the planet's atmosphere and dynamics, including the chemical composition of its clouds. Today, new missions are planned, such as Da Vinci Plus and Veritas, which will study Venus's surface and internal structure. These missions will help answer the question, could Venus have been habitable in the past? Next in line is our home planet, Earth. We'll learn what makes it unique and why it remains the only known home for life. The main thing that sets Earth apart from other planets is the presence of liquid water. About 70% of our planet's surface is covered by oceans, seas, and rivers. Water is the basis of life. Its unique properties, such as high heat capacity and ability to dissolve substances, make it ideal for supporting biological processes. But why does Earth have liquid water while Venus and Mars, for example, do not? The secret lies in the planet's location. Earth is situated in the so-called habitable zone, a region around a star where temperatures allow water to exist in liquid form. If Earth were slightly closer to the Sun, it might have met Venus's fate. And if it were farther away, it would have become a frozen desert like Mars. Equally important is the magnetosphere, the magnetic field that protects our planet from solar wind and cosmic radiation. The magnetosphere is generated by the movement of liquid iron within Earth's core and acts as an invisible shield. Without it, solar wind could strip away our planet's atmosphere, as happened to Mars. Let's recall what solar wind is. It's a stream of charged particles constantly emitted by the Sun. These particles escape from its hot outer layer, called the corona, and travel at speeds up to 800 kilometers per second, spreading throughout the solar system. Solar wind interacts with planets, causing various phenomena. For instance, on Earth, it creates auroras and also interacts with the magnetosphere, protecting us from its destructive effects. Earth is a dynamic planet, and its surface is constantly changing due to plate tectonics. Earth's crust is divided into several large and small tectonic plates that float on the semi-fluid layer of Earth's mantle. These plates move, collide, diverge, and subduct, creating mountains, ocean trenches, and earthquakes. Plate tectonics plays a key role in the planet's material cycles. For example, carbon dioxide released by volcanoes helps maintain the greenhouse effect necessary for retaining heat. Furthermore, plate movement promotes the renewal of Earth's crust, which supports the planet's long-term stability. Volcanoes, in addition to their destructive power, are sources of new materials for Earth's surface. They release gases like carbon dioxide and water vapor, which influence climate, and minerals that enrich the soil. Earth's atmosphere is another unique feature. Its composition is ideally suited for sustaining life. The main components are nitrogen, about 78%, oxygen, about 21%, and small amounts of carbon dioxide, argon, and other gases. This balance is not accidental. It has been shaped by billions of years of biological and geological processes. Oxygen appeared in the atmosphere thanks to ancient microbes that began producing it through photosynthesis. This process, known as the Great Oxidation Event, occurred about 2.5 billion years ago and transformed the planet's chemical composition, making it suitable for complex life. Carbon dioxide, although a small fraction of the atmosphere, plays a crucial role. It regulates the planet's temperature through the greenhouse effect, preventing Earth from freezing. This delicate balance creates comfortable conditions for life, but it is also vulnerable. Any significant changes in carbon dioxide concentration can lead to climatic catastrophes, as happened on Venus. Speaking of our planet, we cannot overlook its faithful companion, the Moon. The Moon is more than just a beautiful object in the night sky. It plays a vital role in Earth's stability and the development of life. The Moon's diameter is about 3,470 kilometers, making it the largest moon in proportion to its planet in the solar system. Firstly, the Moon stabilizes Earth's axial tilt. Thanks to this, the tilt remains relatively constant, ensuring stable seasons and climate. Without the Moon, Earth's axis could wobble, causing drastic climate changes. Secondly, the Moon causes tides. These cyclical movements of water in oceans, seas, and rivers not only affect coastal ecosystems, but also played a crucial role in the evolution of life. Scientists hypothesize that tides may have facilitated the emergence of life on land by providing organisms with an environment to adapt to different conditions. Thirdly, the Moon served as a cosmic shield for Earth, absorbing impacts from asteroids and meteorites in the early history of the solar system. Without it, our planet's surface might have been far more scarred. We not only understand its uniqueness, but also learn to see the fragility of our home. The next planet we will examine is Mars, our closest neighbor, which can tell us about Earth's past and its future. Mars is a planet that has captured humanity's attention since ancient times. Its reddish hue in the night sky inspired myths and associations with war and destruction. But today, Mars symbolizes not war, but hope. It has become a window for us into the past of the solar system and possibly into the future of humanity. Let's understand why Mars is so intriguing. Mars is the fourth planet from the Sun, located at an average distance of 228 million kilometers, equivalent to about 1.52 AU. This makes it almost 1.5 times farther from the Sun than Earth. Consequently, Mars receives significantly less heat and sunlight. In terms of size, Mars is about half the size of Earth, and its surface area is comparable to the landmass of our planet. Mars's mass is only 11% of Earth's mass, and gravity on its surface is about 38% of Earth's. This means that if you weigh 70 kilograms on Earth, you would weigh only 26 kilograms on Mars. Mars is a cold, frozen desert. The average temperature on the planet is -63 degrees Celsius, but depending on the season and location, it can range from -125 degrees at the poles in winter to +20 degrees at the equator in summer. Such sharp fluctuations are due to the thin atmosphere, which barely retains heat. Mars's atmosphere is very tenuous, with a pressure of only 0.6% of Earth's. This is equivalent to conditions at an altitude of 30 kilometers above Earth's surface, 3 times higher than commercial airplanes fly. It is composed of 96% carbon dioxide, with small traces of nitrogen, argon, and minute amounts of oxygen and water. One of Mars's most striking features is its dust storms, which can engulf the entire planet. These storms lift fine dust into the atmosphere, obscuring sunlight and making Mars even colder. The largest recorded storm in 2018 lasted several months and led to the cessation of operations for the Opportunity rover. Yet Mars's surface is extraordinary. Deserts of oxidized iron, colossal volcanoes, ancient dry riverbeds, and ice caps at the poles tell the story of a planet that may have once been very different. Imagine Olympus Mons, the tallest volcano in the solar system, standing 22 kilometers high. That's 3 times taller than Everest, and its base is so vast that you wouldn't be able to see its peak from the surface. Or consider Valles Marineris, a vast canyon system 4,000 kilometers long and up to 7 kilometers deep. That's 10 times longer than the Grand Canyon and 4 times deeper. Scientists believe these features may have been formed by tectonic processes, or possibly by water flows that once coursed across Mars. Yes, water is the key to Mars's mystery. Today, there is no liquid water on its surface, but we see everywhere traces of its presence in the past. Billions of years ago, Mars was warmer, and its atmosphere was denser. Rivers flowed here, lakes formed, and perhaps even an ocean covered a significant portion of its surface. Currently, water on Mars exists only as ice in the polar caps or beneath the surface. However, it is hypothesized that subsurface lakes of liquid water might be hidden beneath layers of frozen soil, especially around the South Pole. These findings offer hope that life may have existed on Mars in the past and perhaps even persists there now. Today, Mars is the primary target for space exploration. Rovers like Curiosity and Perseverance continue to investigate the surface, collecting data on climate, soil composition, and signs of ancient life. Curiosity, operating since 2012, has confirmed that Mars was once habitable, and Perseverance, which arrived in 2020, is studying Jezero Crater, the site of an ancient lake and river delta where microbial life may have thrived. But humanity's ambitions don't end there. Elon Musk and his company SpaceX dream of sending humans to Mars as early as the 2030s to begin establishing the first settlements. Our next stop will be Jupiter, the king of planets, which will show us a completely different cosmic world. Our journey through the solar system continues, and now we leave the zone of rocky planets, heading to where the giants reign. Between Mars and Jupiter lies the asteroid belt, a region filled with millions of rocky and metallic objects that never managed to coalesce into a full-fledged planet. Scientists believe that Jupiter's gravity, the most massive object in our system after the Sun, prevented this. And first to greet us is Jupiter, the most massive and enigmatic planet in the solar system. It is so enormous that it could hold over 1,300 Earths within it. Its influence extends far beyond its orbit. This gaseous colossus not only governs the movement of its moons, but also acts as a cosmic shield, attracting asteroids and comets that could threaten Earth. Jupiter is a world of storms, crushing pressures, and magnetism spanning millions of kilometers. It is inseparable from its perpetual Great Red Spot, incredible auroras, and 4 largest moons, each of which could itself be a separate planet. Its mass is over 318 times that of Earth. But if it continued to accumulate mass, it wouldn't necessarily grow larger. At a certain point, under immense pressure, it would begin to compress, transforming into an increasingly dense sphere. Its gravity is 2.5 times stronger than Earth's. So, if a person miraculously found themselves on Jupiter's surface, they would weigh 2.5 times more. However, standing on a surface would be impossible. It simply doesn't exist. Jupiter is composed primarily of hydrogen and helium, much like the Sun. In its outer clouds, the journey begins through layers of increasingly dense gases. First, an atmosphere filled with swirling ammonia and methane, with hurricanes so vast that hydrogen becomes liquid and then metallic, transforming into a substance that on Earth can only be achieved in laboratories under immense pressures. This is an ocean of metallic hydrogen, tens of thousands of kilometers deep, behaving like a metal and conducting electricity. It is here that Jupiter's incredibly powerful magnetic field is generated, extending millions of kilometers around it. What lies even deeper? Perhaps a small rocky core, roughly the size of Earth, but scientists still debate this. It's quite possible that due to colossal pressure, this core has already partially dissolved into the liquid hydrogen. Jupiter wouldn't be Jupiter without its turbulent atmosphere, characterized by its distinctive bands. These light and dark zones are a result of powerful winds moving in opposite directions at speeds up to 600 kilometers per hour. The planet's entire atmosphere is a boiling ocean of gas, where constant vortices create intricate patterns. Lightning flashes thousands times brighter than on Earth, and pressure in the lower layers compresses gas into a liquid state. And of course, we cannot forget the Great Red Spot, this colossal hurricane, a true veteran among storms. It has been raging for at least 350 years. The storm's diameter today is about 16,000 kilometers, several times larger than Earth, and it's even smaller than it used to be. The spot is slowly shrinking. Scientists are still unsure if it will ever disappear entirely, but this storm remains one of the most impressive phenomena in the solar system. Jupiter's magnetic field is the strongest of all planets, 20,000 times stronger than Earth's. It creates a colossal magnetosphere, so vast that if it were visible, it would occupy more space in the sky than the Moon. Jupiter is a true radiation hell. Streams of charged particles rage around it, and the radiation in its vicinity is deadly even for the most shielded spacecraft. This is why missions like Juno are forced to perform complex maneuvers to avoid the most dangerous zones. Jupiter is not only the gas giant itself, but also its moons. It has over 80 moons in total, but the most famous are the 4 Galilean moons: Io, Europa, Ganymede, and Callisto. Each of them is a distinct world with its own history and unique features. Io is a volcanic inferno. It is the most geologically active object in the solar system. Volcanoes erupt sulfur, coating the moon's surface and making it bright yellow. Its internal structure is heated by gravitational tug-of-war between Jupiter and the other moons. Europa is a world beneath ice. Its surface is covered by an ice crust several kilometers thick, but beneath it lies an ocean of liquid water. And not just any ocean, its volume is greater than all of Earth's oceans combined. Cracks are visible on the surface, caused by Jupiter's tidal forces, and geysers eject streams of water into space. If life exists anywhere in the solar system besides Earth, Europa is one of the prime candidates. But no less captivating is Ganymede, the king of moons. It is larger than the planet Mercury and is the only moon in the solar system with its own magnetic field. Its surface is covered in ice and ancient craters, and it may hide a subsurface ocean within. Callisto is an ancient, crater-covered world. It is one of the oldest objects in the solar system, its surface virtually unchanged over billions of years. Like Ganymede, it may also harbor a hidden ocean beneath its icy crust. Jupiter was the first planet to be studied up close in the 1970s. Pioneer 10 and the Voyagers flew past it, but the most detailed studies were conducted by Galileo in the 1990s and the current Juno mission. Future exploration of Jupiter promises to be even more exciting. In the 2030s, the JUICE mission will travel to Ganymede, Europa, and Callisto to determine if life can exist in their oceans. Jupiter is undoubtedly the king of planets, but its neighbor, Saturn, is no less astonishing. It's a world that seems to embody alien beauty, surrounded by the greatest ring system in the solar system and possessing the moon Titan. What does this enigmatic planet hide? After Jupiter, our path continues towards Saturn, a planet that is truly one of the most beautiful in the solar system. If Jupiter can be called the king of planets in terms of size and power, then Saturn is its aristocratic counterpart, encircled by the most spectacular ring system that makes it one of a kind. Saturn is the second largest planet in the solar system. Its diameter is 120,536 kilometers, more than 9 times larger than Earth's diameter. However, despite its enormous size, Saturn is the least dense planet of all. Its average density is less than that of water, meaning that if there were a large enough ocean, Saturn could float in it. But, of course, its main feature is its majestic rings, which have made it one of the most recognizable planets in the solar system. When we look at pictures of Saturn, the rings appear dense and continuous, like a solid disk. But this is an optical illusion. In reality, they consist of billions of particles of ice and rock orbiting the planet. The size of these particles varies from the tiniest dust grains to house-sized boulders. The thickness of the rings is incredibly small compared to their width, only about 10 meters on average, while their diameter exceeds 200,000 kilometers. Essentially, it's a giant flat disk so thin that in profile it practically disappears. Scientists still debate the origin of the rings. There are several hypotheses. Perhaps they are remnants of a shattered moon that came too close to Saturn and was torn apart by its gravity, or perhaps it's material that simply couldn't coalesce into a full moon due to the planet's own gravitational influence. There are interesting formations within the rings, such as the Cassini division, a huge gap about 4,800 kilometers wide, separating the rings into 2 parts. The culprit behind this gap is Saturn's moon Mimas, which, with its gravitational influence, sweeps particles out of this region. Like Jupiter, Saturn's atmosphere is a mixture of hydrogen and helium, with trace amounts of other gases that give the clouds yellowish and golden hues. But if Jupiter's great red spot draws the most attention, Saturn has an equally enigmatic structure, a hexagonal storm at its north pole. This formation is a true scientific phenomenon. Imagine a giant hurricane 25,000 kilometers wide with a strictly geometric regular hexagonal shape. Within this storm, winds rage at over 500 kilometers per hour, and its edges remain surprisingly sharp, as if drawn with a ruler. Scientists are still unsure why the hurricane has such a shape, but this is not the only atmospheric phenomenon on Saturn. In 2010, its northern hemisphere unexpectedly changed color from bluish to golden. This change was due to photochemical reactions caused by sunlight when summer arrived in that region. Ultraviolet light broke down molecules that gave the atmosphere a blue tint, and the clouds turned yellowish. But Saturn is not just the planet, but also its 83 moons, among which Titan stands out particularly. It is one of the most astonishing objects in the solar system. Titan is the second largest moon after Ganymede. It is larger than Mercury, and it is the only moon with a dense atmosphere. It is this atmosphere that makes it so special. If you were to stand on Titan's surface, the sky above you would be orange-yellow, and plains covered in frozen hydrocarbons would stretch out around you. And the strangest thing is that it rains on Titan, but not water, but liquid methane and ethane. The temperature here is minus 180 degrees Celsius, so water in this world is as hard as rock, and its rivers, lakes, and seas are made of hydrocarbons, which remain liquid at these temperatures. This world remarkably resembles Earth. It has seasons, clouds, precipitation, and its rivers and lakes change with the time of year. We observe some methane seas gradually evaporating, and in other places, new bodies of water appearing. But the most interesting thing is that deep beneath Titan's surface, an ocean of liquid water might be hidden. If so, there could be conditions suitable for life there. While Titan draws attention with its dense atmosphere, another of Saturn's moons, Enceladus, amazes with its geysers. Enceladus is a small world with a diameter of only 500 kilometers, but it has proven to be incredibly active. The Cassini spacecraft discovered that streams of water are ejected from Enceladus's south pole into space, forming entire clouds. These geysers are so powerful that particles from them have formed one of Saturn's rings. Beneath Enceladus's surface lies an ocean of liquid water, and its composition has revealed organic molecules and traces of chemical reactions that could be a source of energy there. This makes Enceladus, along with Europa, one of the main candidates for the search for extraterrestrial life in the solar system. The most detailed studies of Saturn and its moons were conducted by the Cassini-Huygens mission. This probe was launched in the 1990s and spent 13 years in the Saturn system, transmitting thousands of images and unique scientific data. The Huygens probe, detached from Cassini, landed on Titan, becoming the first craft to land on the surface of another planet's moon. It transmitted images of an orange haze, rocky plains, and evidence of ancient rivers. And in 2017, Cassini concluded its mission by plunging into Saturn's atmosphere, transmitting data until the very last moment. Saturn is the last of the gas giants, but it is followed by Uranus and Neptune, icy worlds that hold no less mystery. They possess incredibly powerful winds, strange magnetic fields, and moons that might hide subsurface oceans. After our journey through Saturn's domains, our path continues further into the depths of the solar system, to where the world of ice giants begins. Uranus is the seventh planet from the Sun, and although its size is smaller than Jupiter and Saturn, this planet is astonishing in its uniqueness. It seems to break all the rules, blue, enigmatic, rotating on its side, surrounded by rings and moons with amazing terrain. Its cold, harsh atmosphere hides secrets that still remain largely unexplored. Like Jupiter and Saturn, Uranus is a gas giant, but it has an important distinction. If the two largest worlds in our system consist mainly of hydrogen and helium, then Uranus and its neighbor Neptune belong to a different category: ice giants. What does this mean? The fact is that Uranus has a much higher proportion of heavy elements, such as water, ammonia, and methane, instead of the hot metallic hydrogen found in Jupiter. In the depths of Uranus, a vast layer of ice made of these substances extends. If you could dive into Uranus's sphere, you would first pass through its upper clouds, composed mainly of methane and hydrogen. Then the pressure would increase, and the gases would begin to compress, turning into liquid and icy layers. But if you ask whether Uranus has a solid surface you can stand on, the answer is no. The atmosphere smoothly transitions into the deep layers, and the only thing that can be considered a surface are layers where the pressure is approximately the same as on Earth's surface. At the center of Uranus, there is likely a rocky core, roughly the size of Earth, but covered by a thick layer of hot ice mantle. Temperatures inside can reach 5,000 degrees Celsius, but due to the dense ice layer, the heat barely escapes. By the way, this is precisely why Uranus is one of the coldest planets in the solar system. The average temperature here is minus 224 degrees Celsius, making it even colder than the more distant Neptune. Why is this? Uranus barely emits heat from within, unlike other giants that gradually release energy. Uranus's most astonishing feature is its unusual rotation. Unlike all other planets, which rotate more or less vertically, Uranus is tilted by 98 degrees. This means it literally rolls along its orbit, and its poles either point directly at the Sun or are plunged into complete darkness. This makes the seasonal changes on Uranus the most extreme in the solar system. If on Earth winter and summer change every half year, then on Uranus one pole faces the Sun for 42 consecutive years, followed by 42 years of night. Why did this happen? Scientists believe that during the early stages of its formation, Uranus was impacted by a massive object, possibly a planet the size of Earth. This collision altered its tilt, and now Uranus rotates quite differently from all others. Although Uranus appears as a serene blue ball, its atmosphere is actually highly dynamic. It consists primarily of hydrogen, helium, and 2% methane, and it is the methane that makes Uranus blue, because it absorbs red light and reflects blue and green. Uranus experiences extremely strong winds, reaching up to 900 kilometers per hour, even faster than hurricanes on Earth. Sometimes giant cloud layers appear in the atmosphere, which are very dense. Although rings are associated with Saturn, Uranus also has them.
They are much thinner and darker than its neighbors, and they consist of particles that reflect light.
But the greatest wonders lie hidden among its 27 moons. The most unusual of them is Miranda. This moon looks as if it has been torn apart. Vast rifts, cliffs, and chasms run across its entire surface. Some of the canyons on Miranda are deeper than the Grand Canyon on Earth. Scientists hypothesize that Miranda was once shattered by a powerful collision, but then its fragments reassembled, forming this chaotic world. Currently, the only spacecraft to have ever visited Uranus is Voyager 2 in 1986. It flew past the planet, transmitting the first and only close-up images. Since then, no other craft has visited Uranus, but scientists are planning a new mission, possibly in the 2030s. NASA will send a probe that can study the planet's atmosphere, moons, and internal structure in detail. After the icy and enigmatic Uranus, our journey reaches the last of the solar system's known giants, Neptune. This is the farthest planet, the windiest, and perhaps the most mysterious. Even today, despite modern telescopes and computer models, Neptune remains one of the least explored planets. At first glance, it resembles Uranus, a similar bluish ball hidden under a layer of clouds. But the difference becomes apparent. If Uranus is a quiet and cold world, Neptune is a fierce, stormy giant where the most powerful hurricanes in the solar system rage. This planet is the true master of cosmic winds, and its history is full of enigmas. Neptune is an ice giant, like Uranus, but its atmosphere is more dynamic and far more active. It consists mainly of hydrogen, helium, and methane. It has the same bluish-blue color as Uranus, but the most significant aspect is the winds in Neptune's atmosphere. The strongest hurricanes in the solar system blow here, with wind speeds reaching 2,400 kilometers per hour. That's faster than the speed of sound in Earth's air, and 3 times more powerful than the most destructive hurricanes on Earth. Scientists still don't understand how Neptune maintains such a turbulent atmosphere. The planet receives only 1/9 of the sunlight compared to Jupiter, and its upper layers appear cold and calm. But deeper down, a true inferno of storms and vortices rages at immense speeds. Neptune also has its own giant hurricane, the Great Dark Spot. When Voyager 2 first transmitted an image of Neptune in 1989, scientists saw a massive dark spot resembling Jupiter's storm. It spanned 88,000 kilometers, and the wind speed within the hurricane reached 2,000 kilometers per hour. But when astronomers directed the Hubble telescope at Neptune again a few years later, the dark spot had disappeared. It had simply dissipated. Later, new dark spots were found, other giant hurricanes that appear and vanish in Neptune's atmosphere every 5–10 years. This makes it the only planet in the solar system where immense storms do not persist for centuries, but come and go within decades. Like Uranus, Neptune has no distinct surface. If someone tried to land on it, they would simply sink deeper into layers of gas until the pressure crushed them. Unlike the gas giants Jupiter and Saturn, Neptune has more ice and heavy compounds like water, ammonia, and methane. Beneath its dense atmosphere lies a thick layer of ice mantle, likely composed of water ice, frozen ammonia, and other substances. But beneath this thickness lies an Earth-like core, hot, dense, composed of rock and metals. Temperatures at Neptune's center can reach 7,000 degrees Celsius. It is this hot core that helps maintain the powerful winds and atmospheric activity, as Neptune radiates twice as much heat as it receives from the Sun. Among Neptune's 14 moons, Triton stands out. It is the largest moon of the planet and one of the strangest objects in the solar system. Triton's main peculiarity is its retrograde orbit. Unlike most moons that orbit in the same direction as their planet, Triton orbits in the opposite direction. This means it did not always belong to Neptune, but was captured by its gravity from the Kuiper Belt, a region full of frozen objects beyond Neptune's orbit. But the strangeness doesn't end there. Triton's surface is covered in nitrogen ice, and its temperature is -235 degrees Celsius, making it one of the coldest places in the solar system. However, the most astonishing feature is its ice geysers. Voyager 2 discovered giant jets of nitrogen erupting from Triton's surface. This indicates that deep within the Moon there is a heat source that warms the ice and causes it to sublimate. Some scientists believe that an ocean of liquid water, similar to Europa and Enceladus, might be hidden beneath Triton's icy crust. Currently, the only spacecraft to have ever visited Neptune is Voyager 2. Since then, no other probe has been sent to Neptune, but in recent years, astronomers have been discussing the possibility of a new mission. One project is Neptune Odyssey, which could launch an orbiter to the planet and study it in detail. NASA is also considering the Trident mission, which could travel to Triton and test the hypothesis of a subsurface ocean. However, such missions will take decades. Even if a probe is sent in the coming years, it will only reach Neptune in the 2040s. Our journey through the planets of the solar system has come to an end, but the system itself doesn't stop there. Beyond Neptune lies the Kuiper Belt, which harbors thousands of icy worlds such as Pluto, Haumea, Makemake, and others. We've covered all 8 planets, but between them and beyond them stretches a whole world of small bodies, asteroids, comets, dwarf planets, and meteorites. These objects may seem insignificant compared to giants like Jupiter or Saturn. However, their role in the formation and evolution of the system is immense. They hold information about its distant past, and some of them even pose a potential threat to Earth. When astronomers first began systematically observing the sky, they expected to find another planet between Mars and Jupiter, as according to the laws of celestial mechanics, another large world should have been located there. But instead of one planet, they discovered an entire asteroid belt, a zone filled with millions of small objects that never managed to form a full planet due to Jupiter's gravitational influence. Asteroids vary in size, from giants like Vesta, approximately 525 kilometers in diameter, to tiny fragments barely reaching a few meters. They consist of metals, silicates, carbon compounds, and some even contain water. But besides their scientific value, asteroids pose a real threat to Earth. We know that 66 million years ago, one of them fell on our planet, causing the extinction of the dinosaurs.
Today, astronomers meticulously track potentially hazardous asteroids capable of intersecting Earth's orbit. The largest ones are currently safe, but smaller objects can pose a threat. This is why NASA and other space agencies are developing protective measures, including missions like DART, which successfully altered the orbit of a small asteroid in 2022. For a long time, Pluto was considered the ninth planet of the solar system, but in 2006, astronomers reclassified it as a dwarf planet. This sparked heated debates, as for many, Pluto remained a full-fledged planet.
But why was it demoted? The reason is that it does not dominate its orbit. Other objects like Haumea, Makemake, and Eris are located around it, and they could also claim the title of planet. All of them are located in the Kuiper Belt, a vast region beyond Neptune filled with icy bodies. But despite this, Pluto remains a very interesting object in the solar system. It has 5 moons, the largest of which, Charon, is so large in comparison to Pluto that they form a double system orbiting a common center of mass. Its surface is covered with icy plains and cryovolcanism, similar to what we see on Earth. When the New Horizons probe flew past Pluto in 2015, it transmitted images that astonished scientists. This small world turned out to be much more complex and active than expected. If asteroids are mainly composed of rock and metal, then comets are dirty snowballs made of ice and dust. And when they approach the sun, they begin to melt, forming a tail. This tail always points away from the sun because it is formed by the solar wind, which blows away the vaporized material. Comets come from 2 regions: the Kuiper Belt, our closest source of short-period comets, like the famous Halley's Comet, which returns every 76 years, and the Oort cloud, a vast sphere at the edge of the solar system from which long-period comets like Comet Hale-Bopp originate. Comets played a crucial role in Earth's history. Some scientists believe that they brought water to our planet, and perhaps even the organic molecules necessary for life. And what about meteorites? These are small fragments of asteroids or comets that fall to Earth. Most of them burn up in the atmosphere, creating a beautiful shooting star effect, but some reach the surface. The most famous recent one is the Chelyabinsk meteorite, which entered the atmosphere in 2013, causing a shockwave that shattered thousands of windows in the city. Our journey through the planets of the solar system has concluded. When you think about it, everything we've seen, from tiny Mercury to giant Neptune, exists solely thanks to one object. Without it, there would be no heat, no light, no orbits, and no life. It is the Sun, our stellar energy source, around which the entire system revolves. The Sun is a star. It's not just a hot ball, but a complex and dynamic world where nuclear reactions generate a colossal amount of energy. It is so enormous that its mass accounts for 99.86% of the total mass of the solar system. This means that all the planets, moons, asteroids, and comets combined weigh less than 1/100th of the Sun. But what is this giant star? What processes occur within it, and how does it influence our planet and the entire system? Let's find out. The Sun appears to us as a solid, shining sphere, but in reality, it consists of several layers, each playing its role in generating and distributing energy. The core is the Sun's center, And it is here that the most important processes occur. The temperature in the core reaches 15 million degrees Celsius, and the pressure is 250 billion times greater than on Earth. It is in these infernal conditions that thermonuclear fusion takes place, the process by which hydrogen atoms merge, forming helium and releasing a colossal amount of energy. The radiation zone is the next layer, where the energy produced in the core slowly moves outward. Unlike the core, where everything is boiling and churning, a sense of calm prevails here. Energy is transported in the form of radiation, and photons born in the star's depths can travel through this layer for tens of thousands and sometimes millions of years before emerging. The convection zone is where a different energy transfer process occurs. Instead of photons slowly percolating upwards, hot plasma rises and cold plasma sinks, like boiling water in a pot. It is these currents that give rise to granules and sunspots on the sun's surface. The photosphere is the layer we see from Earth. This is a thin layer, only about 500 kilometers thick in terms of the star's scale. But it is this layer that emits the light that warms and illuminates our planet. The temperature of the photosphere is around 5,500 degrees Celsius, which is relatively cool compared to the core. The chromosphere and corona are the outer layers.
The corona is a vast, superheated cloud of plasma that extends millions of kilometers into space. The Sun is an active and living star where powerful phenomena constantly occur, influencing the entire solar system. Thanks to thermonuclear fusion in the star's core, billions of tons of hydrogen are converted into helium every second, releasing energy equivalent to the detonation of 1 billion hydrogen bombs every second. It is this process that keeps the sun stable and allows it to shine for 4.5 billion years. But the sun is not always calm. Sometimes powerful energy bursts occur on its surface, which can be compared to giant explosions. These flares eject enormous amounts of charged particles into space, and if they are directed towards Earth, they can cause magnetic storms. An even more powerful phenomenon is coronal mass ejections. These are colossal releases of billions of tons of plasma that travel at hundreds of kilometers per second into interplanetary space. If such an ejection hits Earth, it can affect our technology, causing disruptions in satellite communications and power grids. Despite the immense distance from the outer planets, the Sun's influence is felt throughout the entire system. The main mechanisms of this influence are gravity, radiation, and the solar wind. The Sun's gravity keeps all the planets in their orbits. If it disappeared, all planets would instantly fly off into open space.
It is thanks to its gravity that our system has remained stable for billions of years. Solar radiation provides Earth with heat and light, sustaining life. Without this radiation, our planet's surface would freeze and the atmosphere would turn into an icy, lifeless layer. The solar wind is a stream of charged particles emitted by the sun. It spreads out from the sun in all directions, influencing planetary atmospheres, interacting with magnetic fields, and creating auroras. The outermost boundary of solar influence is the heliopause, where the solar wind collides with the interstellar medium.
It is there, 20 billion kilometers from the Sun, that its reign ends and the boundless cosmos begins. The Sun was born 4.5 billion years ago and will continue to shine for about as long. But it is not eternal. In 5 billion years, it will begin to expand, turning into a red giant. Its outer layers will stretch out, engulfing first Mercury, then Venus, and possibly even Earth. And a few 100 million years later, it will shed its outer shells, leaving behind a white dwarf, a small but very dense star. But until that moment, there are still billions of years, and for now, the Sun will remain our primary source of life and energy, that without which our system could not exist. We began our journey through the solar system by studying the planets, but now it becomes clear: everything in our system is connected.
It is an astonishing, complex, and dynamic system in which every planet, moon, and even the farthest comets are linked by invisible threads of gravity, radiation, and energy from our star. Thank you for embarking on this fascinating flight through the expanses of our stellar system with me. I hope this lecture has helped you learn something new, discover amazing facts, and look at space with wonder. If you enjoyed this journey, don't forget to share your impressions, ask questions, and continue exploring the universe. Space is infinite, which means there are many more discoveries ahead of us.